Welcome back, chemists. Today we're going to talk about calculating average atomic mass. So if you remember in our last video, some of our masses on the periodic table, actually all of them, don't add up to be exactly whole numbers. And if your atomic mass is just based on protons plus neutrons, how is that possible? So here's our answer. It turns out to be decimal places because it's a weighted average of all of the isotopes of that element, all the naturally occurring isotopes of that element. So how we do this is we find the sum of the mass of the isotope times its relative abundance. So this symbol right here means sum, meaning you add it all together. And relative abundance is the decimal form of a percent. So if it was 93.1%, to use the relative abundance, we're just going to move the decimal place 2 places to the left. So that would turn out to be 0.931 is your relative abundance. Carbon-12 is what the isotope formula was based on. So one atomic mass unit is equal to 1/12 the mass of a carbon-12 atom. So one carbon-12 is exactly 12 atomic mass units. All right, let's put this math into action. All right, before we start, I want to tell you that I will be working all of the problems on the next page. So I encourage you to pause the video and try the math on your own, and then unpause, check yourself, and make sure that you got it. So the example says that naturally occurring copper consists of 69.17% copper-63, which has an atomic mass of 62.929 AMU, and 30.83% of copper-65, which has an atomic mass of 64.927 AMU. What is the average atomic mass of copper? So what I like to do before I do anything else, and I need you to start this too on your homework because it will save you so much time, is you're going to underline what's given to you. So what's given to us, these are just numbers that you're given. We're given 69.17% copper-63. We are given a mass of 62.929 AMU. We're also given 30.83%, and we're given 64.927 AMU. Now, I didn't underline the 63 or the 65 because those are just part of the name. After you've underlined what you know, you need to circle what you're looking for. What does the question ask you for? So it asks us for the average atomic mass. All right, now that we've annotated all of this, we can actually start doing some work. So remember that our formula was the sum of the mass times the abundance, relative abundance. So we can go ahead here and move our decimal places for our percentages to get that relative abundance. So 69.17%, if we move the decimal place 2 times to the left, this becomes 0.6917 for its relative abundance. And if we do 30.83, 2 decimal places to the left, that becomes 0.3083 for that relative abundance. Now we're just going to take all these numbers and plug them into our formula. All right, you can do this all in one step, or you can do this in multiple steps. But we're going to start with our first mass, which was 62.929 for the copper-63, times that relative abundance, which was 0.6917. And for the copper-65, the mass was 64.927 times our relative abundance, which was 0.3083. Now we can go ahead and calculate these if we want, or we can save it till the very end and put everything into our calculator at once. So we would have 43.5279893 for the 63's total right now, and we would have 20.016991. Now remember that we had the sum of these things, so that means we need to add these numbers together to give us a grand total of 63.544983 for our relative abundance, and AMU would be our unit. But remember, we have to look at significant figures. So significant figures are, we added here, which means we are looking at the least amount of decimal places. So if you look, this has 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 1, 2, 3. So we're going to round this number, our 63 point, all those decimal places, to 3 significant decimal places. So 63.545 AMU. Now, I rounded that to 5 because we had 4 with a 9 behind it. Remember, you only round at the closest decimal following where you're trying to round. So the 9 rounds up to 5, the 4 rounds up to 5 because of the 9. So our final answer is 63.545 AMU for our average atomic mass. All right, so again, I want you to practice on the next one and then watch the work to see what's going on. So our example says naturally occurring chlorine that's put in pools is 75.53% chlorine 35, mass of 34.969 AMU, and 24.47% chlorine 37 with a mass of 36.966 atomic mass units. Calculate the average atomic mass. So first step, always underline what we know, 75.53% with this mass and 24.47% with this mass. Circle what we are trying to find. We are trying to find the average atomic mass. Now, I know we're always trying to find that now, but that's not always how it's going to be. Remember that our formula is the sum of, or adding up all of the mass times relative abundance. So let's go ahead and convert our percents to relative abundances. 75.53%, two places to the left, gives us 0.7553. And 24.47%, two times to the left, gives us, I'll put it over here, 0.2447. All right, so again, relative abundances are just the percents with the decimal place moved two times to the left. All right, now let's start plugging this in. I encourage you to pause and try it. So first we have 34.969 for chlorine 35 times its abundance, which was 0.7553, plus our 36.966 mass times our relative abundance of 24.47%, changed to 0.2447. All right, you could put it in the calculator just like this as long as you use those parentheses that I wrote down. Or you could work it out step by step. So 34.969 times 0.7553 is 26.412087. And 36.966 times 0.2447 is 9.0455802. Remember that our formula is the sum of these two numbers, meaning we're going to add them up. So that will be 35, that's an ugly 3, 0.4576659. Checking significant figures, we added, so we're going to do decimal places, which was 3, 35.458 AMU is our final answer. And look at us go, we are doing math. All right, last example, last chance to pause it and see if you can do it all by yourself. What's the average atomic mass of silicon given the following abundance information of the isotopes of silicon? All right, first we're going to underline what we know. If you look at this question, it didn't give us anything that we actually know. So let's look at that table. Well, silicon 28, it doesn't give us a different mass than that, so we're going to assume that it's a whole number. With 92.21%, silicon 29, 29 is the important part, 4.70%, silicon 30, 3.09%. Every time I see this, it's asking me for the average atomic mass, so I'm going to think about that being the mass times that relative abundance. So let's go ahead and make these into relative abundances by moving the decimal place two times to the left. So it will be 0.9221 for this one. Now, this one's going to be 0.0470. This one's going to be 0.0309. All right, so now we have masses, we have abundances. We're ready to put it all together and make some math happen. All right, first one. We decided we're going with whole numbers because the table doesn't give us any other information. We're going to do 28 times 0.9221. If we want to go ahead and put that in our calculator, we can. We would get 25.8188. And our second mass was 29 times a very small abundance of 0.0470. If we want to go ahead and put that in our calculator, it would give us 1.363. And our last one with the lowest abundance, 0.0309, put that in our calculator, that gives us 0.927. Now I want you to pay attention here. The less abundant it was, the less it's going to be in what we're going to add up. So the 0.03 turned out to be a very, very small number. All right, remember that our formula is the sum, which means we're going to add all of these up to get 28.1088. Checking for our significant figures. Here, we didn't have any decimal places. So the final answer for this is going to have no decimal places. One rounds down or stays the same, so it's going to be 28 AMU for our final answer. And boom, you learned how to do average atomic mass. Great job, chemists. I can't wait to see you next time.